lost in this. And today is no exception. We're going to start pretty straight off with doing quantitative work. So we've been talking about concentration and solutions and molarity. And we can use molarity as a conversion tool because our molarity rates our moles of solute and liters, bless you, of solution. And it can be used to convert relatives amounts, and it can also be used to figure out products and chemical reactions. Oftentimes, our chemical reactions are done in solution, which means that when we're looking at chemical reactions, if we're trying to calculate our percent yield, we need to know how much we started with for our reactant to figure out our limiting reagents and do our reactions. But oftentimes, our two reactants will be in a solution. So we need to know how much of each reactant we have. We know how much of each solution we're adding. We might measure out a couple of milliliters of a certain concentration of solution. So we need to be able to convert that to calculate things like our expected yield, our percent yield, to even figure out if I'm reacting two compounds and I have 1 milliliter of a solution of a certain concentration, how much of the other compound do I need to fully react it? So I need to be able to use these in chemical reactions for our stoichiometry. Now remember, our molarity is just a relationship, so this isn't really adding too much, but a different layer, a different relationship to do our conversions. So if we know our volume of a certain solution, we can calculate the moles that we have in that solution because our molarity relates moles to liter solution. And then we can figure out our moles of our product, or how much moles of a reactant we need, whatever we're doing, like we did in our stoichiometry last time, to figure out the volume that either we're going to make or we're going to form. So there's a lot of things that we can do with this. So let's look at an example. So let's say we want to know what volume of a certain concentration of KCl is required to completely react with 0.150 liters of PbNO3 of a certain concentration. So that means that I have a certain amount of liters of this concentration of reactant 2, and I want to know how much of reactant 1 I need to fully react. And remember, I need to do that with moles, and I need to use my stoichiometry of my equation. So first off, I'm given my concentration of my KCl solution that I have available. And don't just write down 0.150 molar, write down 0.150 molar KCl solution. Because that is the concentration of KCl solution. That's not the concentration of anything else that we have. So that's very important. That relationship is only relating moles of KCl to liters of that solution. I also know the value of PbNO3 I have, and I know the concentration of that solution. And again, don't write down 0.175 moles. Write down 0.175 moles PbNO3, so you don't get lost as to what solution is what. That means we have two different solutions, and they have two different concentrations with two different solutes in them. So I'm going to be mixing them to do a reaction. And remember, our relationship of our periodic table tells me for a full reaction, I need 2 moles of KCl for every 1 mole of PbNO3. If I had given you moles of KCl and moles of PbNO3, you'd already know how to do this. So the only difference here is we're adding a layer in the fact that we have 2 solutions of a certain concentration. And that is our relationship. So our given is that we have a solution of KCl, bless you, that has 0.150 moles per liter. And then I know I have 0.150 liters of PbNO3 and 0.175 moles of PbNO3 per every liter of that solution. So that's what I'm using, and I'm trying to find the volume of KCl I need to completely react with my PbNO3. So that's what I'm finding. So my relationships, I know I have 1 liter of PbNO3 for every 0.175 moles of PbNO3 because that's what my molarity tells me. That is my concentration. I know I have 1 liter of KCl equals 0.150 moles because that's what my molarity of my KCl solution tells me. So those are my relationships. I cannot use this relationship to figure out my liters directly of KCl because this is my relationship for my PbNO3 solution only. That's important. And then I also know based on my reaction that I need 1 mole of PbNO3 too for every 2 moles of KCl. And that tells me that based on this balanced equation. And again, always make sure your equation is balanced, but it is in this case. So those are my relationships. I don't need to convert to mass at all because remember I'm using the mole relationship based on my stoichiometry of my reaction. So my conceptual plan, I need to figure out how much moles of PbNO3 I have in 0.150 liters because that's how much of that solution I'm using. So that's my first step. I'm going to take my 0.150 liters of my PbNO3 solution and figure out how much moles of my solute I actually have. And I can do that using my molarity. Once I know my moles of this, I know based on my reaction, 1 mole of this, I need 2 moles of KCl to react with it. That's based on my chemical equation. So I can convert that. And that'll tell me how many moles of KCl I need to react with the volume of this solution I'm using. Once I do that, then I just need to figure out, well, how much of my other solution do I need? Because my other solution tells me that for every 1 liter of KCl, I have 0.150 moles. Remember, I can't just measure out moles, but I can measure out my milliliters or liters of solution. So that's my last step. And of course, I'm giving this in liters. Remember, my molarity is in moles per liter. But in the lab, I might actually be measuring out milliliters. So just keep paying attention what volume I'm asking for. So that's how we're going to set it up. So we know that we have 0.150 liters of my PbNO3 solution. I don't know how many moles that is unless if I have my specific concentration. So I'm going to use my concentration that relates my liters of PbNO3 solution to my moles of PbNO3. My liters are going to go at the bottom so it cancels out. And remember, this relationship is only for this solution. And I got this relationship from my molarity. So this gives me my moles of PbNO3 too that I have when I have 0.150 liters of that solution. And then I know based on my equation that I need 1 mole of PbNO3 reacts with 2 moles of KCl to form our product. So I need to do this step to figure out how many moles of KCl I need. Once I know how many moles of KCl I need, now I need to figure out how many liters of the solution of the concentration of KCl that I have. So that's based on my molarity of my second solution. So my mole KCl cancels out, and that's going to be left with liters. Now I can convert this to milliliters if I need to, bless you. But in this case, they're not being specific as to what volume, they just want to know what volume. So liters is a volume, and that's perfectly fine. So what I need is, I'm going to have to measure out 0.350 liters of my KCl solution and mix that with my 0.150 liters of PbNO3 and that will give me a full reaction. Again, that's with that molarity concentration that we're given. Your molarity is your relationship. And again, your molarity of PbNO3 can only be used to convert your moles of PbNO3 to liters, or liters of PbNO3 solution to moles. You cannot mix those relationships. Those are very specific relationships. If I change my concentration, I have a new relationship. Let's go over one more example. Here, I have 43.8 milliliters of a 0.107 molar HCl solution. And I'm told I need that much to neutralize 37.6 molar BaOH2 solution. What is the molarity of my base? Well, my barium hydroxide is my base, and we're going to talk about that in a second, in a couple of slides when we talk about acids and bases. And when we're talking about an acid-base reaction, neutralizing just means that we did the full reaction. We reacted all of my BaOH2 with HCl to form barium chloride and H2. So that's all that means. So what this tells me is I have an unknown concentration of a barium hydroxide solution. And I know how much volume I have, but I don't know my concentration. But I do know that it took 43.8 milliliters of a certain concentration HCl solution to neutralize it until it stopped reacting. So that means I can figure out my molarity of my barium hydroxide solution because I know my stoichiometry of my reaction. I know it takes 2 moles of HCl to react with 1 mole of barium hydroxide. I know that based on my chemical equation. So I can do this calculation because I know everything I need to. I know how much HCl I needed, and I know what concentration that HCl was. And this is common in the lab. And you'll do this when you do take lab because it's hard sometimes to calculate your molarity or your concentration of a base. Because bases tend to pull in water from the air, which affects the concentration. So we'll often do this. This is typically called a titration. We'll talk a bit more about that as well later on when we really get into the reaction. But we're given everything we need. So we're given our volume of HCl and our concentration of HCl. We're given our volume of barium hydroxide. What we don't have is our concentration. Again, that molarity is the molarity for our HCl solution. Don't just write down 0.107 mole. Write down 0.107 moles HCl. That's only my relationship from HCl volume and HCl of the solution. That's not a relationship between anything else. So make sure you write that HCl so you don't get lost as to what concentration this is for. That's only for that HCl solution. And then I'm finding my concentration of my barium hydroxide solution. So my conceptual plan is that I know my volume of HCl. It's in milliliters. I can convert that to liters. If I know my volume of HCl and I know my concentration of HCl, I can figure out how much moles of HCl I use to react with my barium hydroxide. So once I know my moles, I have my relationship between how much moles of HCl I need for every mole of barium hydroxide based on my reaction. So I can figure out my moles of BaOH2 that I had present, because that's how much HCl I needed to react with it. I also know my liters of solution. Well, I know my milliliters of solution. I'm going to have to convert it to liters. And remember, my molarity is just moles over liter. So I can calculate my concentration of my barium hydroxide solution by doing this. And then I have my relationships. I know it takes 1,000 milliliters for every liter. That's just my relationship we need to know. And I always do this step. I know a lot of you move the decimal place. As long as it's correct and you're moving at the right amount of spaces, that's fine. I also know, based on my concentration of HCl, that is 0.107 molar, that I have 0.107 moles of HCl for every 1 liter of HCl solution. And then I know from my reaction that I have 1 mole of barium hydroxide reacts with 2 moles of HCl for a complete reaction. So the first thing we need to do, we need our liters of HCl, because our molarity, our concentration relationship is in liters. And don't put down 37.6 milliliters to start, because that's my milliliters of barium hydroxide. So I need my milliliters of HCl, so I know how many moles of HCl that I used. This is important. Make sure you're paying attention to what you're given and what each volume is for. If this is volumes of HCl solution, I need to make sure that that 43.8 is tied with my HCl. That's a common mistake, mixing up your volumes. Everything's in volume, so don't mix up which each volume is for. So to figure out how many moles of HCl that was in 43.8 milliliters of my solution, I can use my molarity. But first I need to calculate this to moles. Liters. So my 1 liter HCl solution goes at the bottom, so it cancels out. And my mole HCl goes on the top. So now I know how many moles of HCl that I had in that 43.8 milliliters. So I want to know then how much moles of barium hydroxide I must have had, because I know my relationship on my reaction. So 2 moles of HCl is going to react with 1 mole of barium hydroxide according to my chemical reaction. So this will give me how many moles of barium hydroxide I had in 37.6 milliliters, because I know how much HCl reacts with barium hydroxide based on my chemical equation. But this wants our concentration. Remember, our concentration is just our mole over liter. We have milliliters of barium hydroxide, so we have to convert that to liters of barium hydroxide, because this is our molar relationship. So we have our moles of barium hydroxide, we just figured that out. Now we need to figure out our volume in liters. If your volume's already in liters, you don't have to do anything else. But in this case, it's not. So now I have my moles. Now I have my volume in liters. I can figure out my molarity. And this is very common calculation we have to do in the lab, especially when we're determining concentration of a base. And you'll be doing this a lot in your general chemistry labs when you take 110, or if you're in 113 and 114 if you're a chem major. And if you do take quantitative analysis, you're going to be doing this a lot. So we haven't really talked about our chemical reactions too much yet, but we'll be applying this more when we talk about our chemical reactions. Again, when you're working with molarity and volume, make sure that you're not mixing which concentration solution is with what. You have to really make sure you're writing things down correctly and reading what it's giving you clearly. Yes?
When I plug that in my calculator, I got something good.
Now this should be right. This should be correct. Oh. Yeah, that's what I get when I plug mine in. Yeah, I round when you plug it in your calculator, don't round it too early. I'm not writing all the numbers here. When I put it in my calculator, I don't round. I just divide it straight away by this. So make sure you're not rounding too early. But that's correct. That's the correct answer. So don't round too early. Okay. I don't have a lot of room to put all those numbers. So we've talked a bit about concentrations and reactions. Now we're going to get more into what actually happens when things dissolve and start talking about chemical equations that occur when we look at reactions in aqueous solution mostly, which is what we'll be looking at in this chapter. So there's attractive forces between our solute particles that hold them together. We call those intermolecular forces, meaning forces between different molecules. And we're going to get into that a bit more in later chapters. I find this book is a little disjointed, but this is the book that everyone agrees upon, so I have to go with it. But there's a couple of these forces that we'll talk about, but there's an inner force that's keeping our molecules together. For the most part, what we'll be talking about with ionic bonds is going to be that positive and negative charge attracting each other. So we call that an ionic charge and an ionic bond. There's also attractive forces between our solvent molecules. If we're talking about water, each water molecule is attracted to another water molecule. That's why it's in the solvent in the aqueous or liquid phase. When a molecule goes into the gas phase, their intermolecular forces aren't really attracting each other anymore, which is why they're not held very closely together and they're in a different phase. And in the solid phase, those intermolecular forces are even stronger. That's why it's in that solid amount. But what we'll mostly be talking about is in solution. So, the solvent molecules are attracted to each other. For a solvent to dissolve a solute, the intermolecular forces between the solvent and the different components of the solute have to be stronger than the intermolecular forces between the, in our case, ions, and the intermolecular forces between our solvent molecules. Otherwise, dissolving will not occur. In an ionic solution, when we dissolve, we break up our interaction between our positive charge and our negative charges. Because then our positive charges and our negative charges will be more attracted to water than it'll be attracted to each other. And that way, in the case of sodium chloride, we'll pull sodium chloride apart. Water will surround the sodium ions and the chlorine ions, and therefore it'll be in the same state as the water. So we have to have a greater interaction between our solvent and our solute than our solvent and solvent or our solute and solute. In some cases that happens, in some cases it doesn't. If they're strong enough, our solute will dissolve. So when we look at an ionic compound, this is representing something more like sodium chloride. Of course, we know we might have +2, -1, different things like that, but this is just relating. And as you can see, your water is going to surround your different ions, pulling them apart from the solid and putting them in their solution. That's what we're going to see mostly in this chapter because we're working with aqueous solutions. But there are other cases where dissolving can occur. This isn't quite the same thing that happens in something like dissolving sugar, because sugar is not an ionic compound, sugar is a covalent compound. So our covalent compounds are a little bit different. But the same concepts are there. So the result is that we have free ions moving within our solution. So when we're talking about ionic compounds that dissolve, they tend to conduct electricity, because now we have free charge moving around in solution. What if I told you water does not conduct electricity? Do you believe me? It's true, water does not conduct electricity. However, tap water has a lot of dissolved ions in it, and the ions conduct electricity. If you have a pure sample of water, only H2O, that's a molecular compound, it will not conduct electricity. So for a solution to conduct electricity, we need ions. If I took pure water and I dissolved sugar in it, it also would not conduct electricity. So we're going to look at that. Solutions that conduct electricity, we call those electrolytes. That makes sense. If we take pure water and we dissolve salt in it, we can in fact conduct electricity. And of course, almost all of our tap water has dissolved ions in it, so you definitely don't want to put your blow dryer when it's plugged in your bathtub. It's not a good idea. But if you had a bathtub of pure water, you could do it. It wouldn't conduct electricity. It would still break your blow dryer, however. So materials that dissolve in water to form a solution that don't conduct electricity, we call those non-electrolytes. Not really a common term used as much. Electrolytes is used a lot more. So electrolytes have dissolved ions in our solution. But sugar isn't a dissolved ion. So what happens when sugar dissolves? When sugar dissolves, it doesn't dissolve as a charged particle. But when ions dissolve, it does. So we have a bunch of charged particles floating around in our solution, and electricity is just electrons. So electrons can be conducted through the fact that we have those charged particles. Non-electrolytes like sugar are typically from molecular compounds that don't have a formal charge. Our whole compound is neutral. And when we dissolve something like sugar, our sugar can interact with those sugar molecules through those intermolecular forces. And when we put it in water, water will interact with sugar molecules more than the sugar molecules interact with each other. So water will pull the sugar molecules apart from the solid crystal, which is how we usually call those crystals. However, each individual molecule stays intact, unlike ionic bonds where we are actually pulling the ionic bond apart. With molecules, each covalent bond stays intact when it's in water. So we don't form any charges. So our full molecule might be surrounded by water, but we still don't have any charges because the molecule is not broken. Dissolving does not break covalent bonds. But dissolving does pull apart our interaction between our positive charge and our negative charge in ionic bonds. So that's our difference. There are exceptions, the most notable being molecular acids. The most notable one that we've talked about is the acetate ion. That is a molecular acid because the hydrogen can be pulled apart from the oxygen to form H plus and O negative. There's other molecular acids when you take organic chemistry you'll learn about, but the one we really learned about with our polyatomic ions was the acetate ion. So that one will conduct electricity, though sometimes not as strongly. The molecular acids aren't always a very strong conductor of electricity. That also brings you to the fact that not all dissolved ions conduct electricity as strongly. It depends on the amount that the ion is dissolved. So some things don't dissolve as easily, they won't conduct electricity as well. So if we're looking at these, the one that would conduct electricity is this one because this is our only ionic compound. Assuming it dissolves, and we're going to talk about solubility rules next, assuming it dissolves, then it's going to conduct electricity. Sugar is a molecular compound, and it doesn't form ions in solution. Ethanol is also a molecular compound, and does not form ions in solution. And O2 is a molecular compound. Those are all covalent bonds, so they don't form ions in solution. So the only one that conducts electricity are the ionic compounds that dissolve. So acids are molecular compounds that ionize when they dissolve in water, and they can conduct electricity. So like I said, the acetate ion. We actually do form ions in water. Typically, the molecules are pulled apart where our acid forms H+, and then our carbon-containing molecule usually has a negative charge somewhere on it. Now, depending on how strong the acid is and how much it ionizes in water, that depends on how much ions actually form when it dissolves, and that affects your amount of conductivity. The less dissolved ions you have, the less conductivity you have. So that makes sense. So for example, HCl is one of our strong acids, and it fully ionizes to form H plus and Cl minus. So it's going to conduct electricity a lot better than something like a weak acid like HF, which doesn't fully ionize. And if you look at this equation, you might notice that here I have an arrow that goes straight forward, whereas here I have a double arrow. That represents an equilibrium. At some point, we're going to have an equilibrium between my concentration of my reactants and my concentration of products, which means we never have full H plus F negative. We have a relationship between HF and H plus and F negative. So that's not going to conduct electricity as well as the same concentration of HCl because we have more ions in this solution. So the stronger the acid, the more conducting. So that brings us to the concept of strong and weak electrolytes. Strong electrolytes are material that dissolve completely as ions. So ionic compounds that are soluble are usually strong electrolytes, as well as strong acids. And they're going to conduct electricity very well. Weak electrolytes are materials that dissolve mostly as molecules, but might have a small amount of ions. Or if we just have a partial solubility, those are going to be weaker. Weak acids, which are everything other than the 5 strong acids we're going to learn about, those are only partially ions, and they might conduct electricity, but not very well. Things like our acetic acid. Acetate ion, acetic acid isn't a strong acid, so therefore it's not going to conduct electricity as well as something like HCl. Again, the concentration of dissolved ions is also a factor. So we're talking about if we have the same concentration. So what happens when we call this dissociation, this ionization, or dissolving? So when an ionic compound dissolves in water, the anions and cations are separated from each other. And we're going to mostly be talking about ionic compounds. We'll get into acids and bases. We won't really be talking too much in this class about molecular compounds that don't ionize in water. That's more your organic chemistry. That's 2 whole semesters of reactions of covalent compounds. We won't be talking about that too much in here. We're going to mostly talk about ionic compounds. So when our ions, our anions and cations are separated from each other and surrounded by water, we call that dissociation. So if we took Na2S and we put it in water, we know it's in the water state by putting that AQ. The AQ means aqueous, meaning it's dissolved in water. So anytime you see AQ, that means dissolved in water. We've seen that with acids, but that can also be true here. So we made a solution of Na2S. So when it dissolves in water, what we're forming is Na plus and S2 minus. So this is just showing our ions with the charge predicted from the periodic table. Unless, of course, we're talking about a variant charge, then we have to look at what the charge is based on our formula. We've done this all before, especially when we talked about naming, so this isn't new. If it dissolves, then we'll put AQ before each ion. So that's what our dissociation looks like. With complete dissociation, we'll show an arrow going forward. When compounds containing polyatomic ions dissociate, we only break it up based on the ion. We're not breaking up the covalent bonds in the polyatomic ion. So if we look at SO4 2- for Na2SO4, our bond between sulfur and our 4 oxygens, that's covalent bonds. So we're not breaking those. That polyatomic ion stays together. So when it dissolves, we're going to form Na plus, of course, and it's +1 based on where it is in the periodic table. And we're going to form our SO4 2-. We're not going to form S2- and O2- because dissolving is not breaking those covalent bonds between my sulfur, my oxygen, and my polyatomic ion. We're just breaking apart the anion of my SO4 2- and my cation. And notice our complete dissociation equation is balanced. So in both cases, we had to balance it. We have Na2S, so we form Na plus ions and S2-. But to fully represent this equation, we need to balance it. We have 2 sodiums here, so we must have 2 sodiums here. We have 1 sulfur. We have 1 sulfur. So it is balanced. So when you're writing these dissociation equations, you must show it as a balanced equation. Same thing in the next one. We have 2 sulfurs. 2 sodiums. We have 2 sodiums. We have 1 sulfur. We still have 1 sulfur. We have 4 oxygens. So it is balanced on both sides of the dissociation equation. Now another note, this is not necessarily a reaction. What we're representing is dissolving. So if I were to take this solution and evaporate all the water, then what I'd get is a crystal of Na2SO4. So that's not changing. A reaction will not occur until I mix these 2 solutions together. So technically this isn't a chemical reaction, this is just a change in state, but we're representing the ions that we're separating. Now when a strong acid dissolves in water, then we show it ionizing to H plus and whatever the anion is. So if we talk about HCl, it would be H plus and Cl minus. Here we're looking at H2SO4, so it'll be H plus and SO4 2-. And then of course we have to balance the equation. Here we have 2 hydrogens, so we must have 2 hydrogens once it dissolves. The amount of hydrogens in the solution is not changing. That's why we need to balance it. Notice we're not showing any water. We know water is dissolving it because we have that AQ. That means that it's dissolved in water. So we're not actually showing the water in these dissociation equations. It's understood water is there based on this. So let's look at writing the equations for the process of dissolving these strong electrolytes. So we have CaCl2. So the first thing, if we're dissolving in water, we're going to put the AQ behind it. You have to have the AQ. It represents it's not a solid, but it's dissolved in water. So that's going to form my 2 ions. So I have my calcium ion and my chlorine ions. Calcium's in the first column in the periodic table. So, second. So it's Ca2 plus And then I put my AQ, representing that it's dissolved in water. And then chlorines in group 6, so it's Cl minus. That's nothing different. We already learned how to figure out the charges. Now my last step is it balanced? And right now, the way it's written, it's not, because I have 1 calcium on both sides, but I have 2 chlorines, and I only have 1 chlorine. So I must balance it. The amount of chlorine atoms here is not changeable, so I have to represent that. So this is my full dissociation equation, what it looks like when it dissolves in water. Looking at the next one, HNO3, that's an acid. So my HNO3 is going to form H+. Again, I need my AQ, and all of these representing it's dissolved in water. And then my NO3 is my polyatomic ion, so we're not breaking up my nitrogen and my oxygen. That is covalent bonds. But instead, it's forming my NO3 ion, NO3 1-. And again, the AQ is necessary. The last step, is it balanced? And in this case, it is. Everything is balanced. I don't need to do anything else because it's already balanced. So that's what my dissociation equation looks like there. Lastly, we have NH4, 2CO3. That's 2 polyatomic ions, and you still need to remember that and recognize them. So we have my ammonium ion and my CO3 ion. So again, my first step, writing that with aqueous behind it, because that represents it's dissolved in water. My NH4 ion is an H4+, and again, aqueous. Plus my carbonate, CO3 2- ion, again, aqueous. I'm not breaking up my polyatomic ions. I'm just breaking up my anion and my cation. My last step is to, of course, balance it. So here I have 2 nitrogens and 8 hydrogens. And here I only have 1 and 4. So it's not balanced. I need to balance it. So your last step is always balancing that. So these are my dissociation processes. Again, this isn't actually really considered a chemical reaction. If I were to evaporate the water, I'd reform my salts. So now we have to talk about when things are soluble and when they're not. Is it not going through? Okay, hold on. I must have... There we go. Okay. Why does it keep on changing? Alright, sorry about that. Sometimes the iClicker has a mind of its own.
Alright, there we go.
So how do we determine solubility? Well, some ionic like sodium chloride, dissolve really easily in water at room temperature. Other ionic compounds like silver chloride dissolve hardly at all at room temperature. And maybe we have to heat them up to dissolve, or maybe they never dissolve. So how do you know if a compound is soluble or insoluble if it's not dissolving in water? Well, the degree of solubility sometimes depends on temperature. When we raise the temperature of a solvent, that means we have more molecular movement, so sometimes that allows something to dissolve. Sometimes it doesn't. Some compounds just will not dissolve in water. Again, it has to do with the ionic strength between our anion and our cation versus the strength that it would have interacting with water. And if the strength between the anion and cation are stronger than the interaction between water, it's not going to dissolve. So how do you know? Well, as some compounds dissolve very little, but just not enough to matter. So we consider them virtually insoluble. So predicting it, if you don't know the rules we're going to learn, can be difficult. You can take different compounds and in the lab try to dissolve them and write notes down, which is what was originally done. Now you have rules that you can follow, and you don't have to take a bunch of salts and try to figure out if they dissolve, because someone did it before you and reported the results. But that's the way you can do that with experimental results. That's your empirical method, taking a bunch of different salts, seeing if they dissolve. If they don't dissolve, then you write that down. But now we have rules that we're going to follow, and you need to know these. So here's our solubility rules. So you must know these, and there's these rules. So here are these compounds that contain these ions are generally soluble, with exceptions. So let's go through this. So typically, lithium, sodium, and potassium, that's all our +1 ions in the first row of the first column of the periodic table. And NH4 plus, pretty much soluble no matter what they are interacting with. So we're talking about in water. Let's make sure the solubility rules are based on aqueous solutions, not if we're in organic chemistry talking about nonpolar solvents. So that right there, we're talking about in water for these solubility rules. So no exceptions. If you see a ionic compound that has lithium, sodium, potassium, or ammonium ion, then it's going to be soluble. Now, NO3 minus and our acetate ion also are pretty soluble, no matter what they are attached to. So we don't have any exceptions. Our halogens, chlorine, bromine, and iodine being the ones that we use the most, chlorine, bromine, and iodine are pretty much soluble with everything except silver, mercury, and lead. So know those rules. Anytime you see chlorine, iodine, or bromine, they're soluble with these exceptions. Now we're talking about ions, not bromine, chlorine, or iodine bonded to a non-metal. So that is a molecular bond. We're talking about ionic bonds. And then SO4 2- is generally soluble, but again, not with silver. Silver is problematic, and so is lead. You'll see that often. But also not with our column 2 metals either. So SO4 2- is not soluble when it's attached to calcium, strontium, and barium. Those are all in that second column in the periodic table. Now these compounds are generally insoluble with exceptions. So our OH- ions are generally insoluble, except for when they're bounded to lithium, sodium, potassium, NH4+. Remember, those are the ones that had no exceptions, so that makes sense. OH- is still no exception. And then also calcium, strontium, and barium. So our hydroxide can be, that's our OH-, it's called hydroxide. Can be bound, causes our base typically, to also those second column ions. S2-, our sulfur ion, is generally not soluble, again, except for when our exceptions, and again, that second row. So pretty much first row, second row, and ammonium ion. So fairly straightforward. Ca3 2- and PO4 3-, again, the exception is the fact that Everything in that first column is soluble in everything. And ammonia. So if we're looking at these, and this is the last thing I'll go over today, and then we'll talk about the actual doing reactions. KOH, potassium's in that first row, it's soluble. Because it contains K+. So it will dissolve in aqueous solution. AgBr, Br minus is not soluble when it comes into contact with silver, so that would be insoluble. It would not dissolve in aqueous, so it would only ever have an S, not AQ, because it doesn't dissolve. CaCl2, Cl minus, it's fine. It's soluble. Its only exceptions are silver, mercury, and lead. Calcium is not silver, mercury, or lead, so it is soluble. Our NO3 minus, and our Pb, our lead. It contains NO3 minus. We don't have any exceptions with NO3 minus, so therefore lead is fine. And PbSO4, SO4 2 minus is generally soluble except for when it's attached to lead 2+, so it is insoluble. So you need to know your solubility rules. And usually when I'm going over ones in class, I'll have these there so you can follow them when you're going through your notes. So of course our answer here is C. So go through those. Y'all have a good day. See you on Wednesday.